Alright, we're going to get started. This is the last theory lunch talk of the semester. If you're interested in giving a talk next semester, talk to Nama Ben David or Nick Gresh. And so now we have Vijay talking about polynomial optimization over the unit sphere.
Alright, hi guys. Yeah, that's what I'll be talking about, and this is joint work with Mrinal Ghosh, Venkat, Uyung, and Madhur Tulsiani. Alright, let's begin. So we start with like a famous old standard problem where you have a homogeneous quadratic polynomial in n variables. Here by homogeneous, I mean that every term has every monomial has the same degree, specifically 2 in this case. Okay, and then you want to maximize its absolute value over the unit sphere. Okay, and this problem is just equivalent to finding the spectral norm of a matrix. Okay, where this matrix, its ijth entry is defined as the coefficient of xi times xj in this polynomial key, divided by 2. Because the matrix has ij and ji, so you want to ensure that x transpose mx is equal to q of x.
What's the norm on the x?
The 2 norm. Yeah. The L2 length. Yeah. Right. So this is just the spectral norm of a matrix, and this can be done in polynomial time. So today we're going to study a natural generalization of this question. Specifically, you're given a homogeneous n-variate degree d polynomial, and you want to maximize this over the hypersphere. And so here's what's known about the problem. It's NP hard to approximate to within 1 plus 1 over poly of n. I think this hardness should be improved. And this is due to Nesterov and also another paper due to Barak et al. It's also hard, assuming the exponential time hypothesis, to approximate to within 2 to the root log n. Okay, so this is approaching polynomial in hardness. So what's the best polytime algorithm we know? Well, n over log n to the d over 2 minus 1. And yeah, this is due to Alexander Manchoso, and a lot of the ideas were already known to Court and Nauer in a paper of theirs in 2008. Okay, so we want to study this problem from the lens of sub-exponential algorithms. So we want to see, if I give you more time, how much can you improve this approximation factor? Because clearly it's not very good. Yeah, so as a function of q, if I take n to the q time, what can I do? If you don't know what the SOS hierarchy is, don't worry. I'm just going to mention this word like 3 or 4 times in this talk, and I'm not going to define it. But yeah, specifically our algorithm works on the SOS hierarchy, but I'll try and keep this talk independent of this. Okay, so why do we study this problem? Well, it's a pretty fundamental problem, just like the eigenvalue problem. So as a result, it has many connections to quantum information theory and like to the unique games conjecture, tensor decomposition, refuting random CSPs, etc. And our very own Alan showed a connection to Planet Quake. All right. So the other reason we study this is because we sort of want to figure out techniques for analyzing polynomial optimization in general, specifically sub-exponential algorithms, and we feel these techniques are sort of best tested on this setting because in some sense, the hypersphere constraint is one of the simplest non-convex problems you could try and solve. Okay, so we like to test analysis techniques on this first. Okay, so this is what we prove. Specifically in n to the q time, given an arbitrary homogeneous degree d polynomial f, we show that you can approximate its 2 norm, which is what which is the maximum over the hypersphere, to within a factor of n over q to the d over 2 minus 1. If you're not able to get a feel for this bound yet, don't worry about it. Hopefully soon enough this will become more clear. Yeah, and also we consider the class of non-negative coefficient polynomials. And then we get an n over q, literally the square root of the previous approximation factor. And lastly,
I completely forgot what q is.
Oh, so in n to the q time, you can do this.
Oh, I see. Okay.
Yeah. So lastly, we consider random polynomials. Like specifically, every coefficient is IIT plus minus 1. Right? And then here you need to be a little careful about how you state what you get. But the point is you still get an n over q to the d over 4 minus half approximation. So note that this approximation actually matches the non-negative coefficient approximation, which is quite strange. I mean, it seems to suggest that this problem is even hard on the average case. Yeah. Okay, so related work. Doherty and Venner analyzed the SOS hierarchy on this problem of maximizing a polynomial over the hypersphere, and they showed for arbitrary f, like once you're past linear levels, or like once you take n to the n runtime, it starts converging very quickly. But we actually want to analyze this when q is much less than n. Okay. Now the case for non-negative coefficient polynomials was also considered by Barak, Kellner, and Strider in, I believe, 2014. And they give a bound that is hard to compare with the multiplicative approximation. So in some sense, our results are incomparable. Assuming a reasonable conjecture, though, I believe in the worst case, we improve on their bounds. Okay, lastly, the random result was also independently obtained by Raghavendra Rao and Shram. They put a slightly weaker version of this. And that's it for my slides. I want to start proving things, so I'm going to get to the whiteboard. How do I retract this?
You don't need it again, right?
No, I don't. It's good. All right. We'll have to start with some definitions before I state the algorithm. So before that, I'm going to state what I'll try and prove today. So today I'll focus on the case of non-negative coefficient polynomials, so which I'll abbreviate as NNC. NNC degree 4. I'll focus on degree 4, and for some reason even is easier to consider, so I'll do that. So this is the smallest even number larger than 2, and that's why I'm considering it. And unless otherwise specified, every polynomial in this talk is homogeneous. Okay, so given a non-negative coefficient degree 4 polynomial f, we're going to show how in n to the q time you can approximate the 2 norm of f to within n over q. So note that this is slightly weaker than what I claimed on the slides, just because this is going to be easier to prove. Yeah. So the slides implied that we can actually prove this, but today I'll just show this. All right. So yeah, again, before I state the algorithm, I need to start with some notation. Specifically, I'm going to write a polynomial f of x as a summation. So f alpha is the coefficient of a multi-index alpha, and x to the alpha is defined as follows. Yeah. So I've written a bunch of notation regarding multi-indices over here. Hopefully people can see it and refer to it in the talk later on. But yeah, basically you should think of a multi-index alpha as equivalent to a multiset. It represents a multiset, but the ith entry of alpha stores the multiplicity of that element in the multiset. Okay, and I'll use this to denote the number of elements in the multiset. This is just summation of alpha I. Okay.
There's no dimension in your theorem, is that because it doesn't matter? Or, wait, n is a dimension.
Yeah, n is dimension, yeah. Yeah. It's an n-variate polynomial, n is dimension. Okay. Right, so let's try and follow through on the same intuition from the quadratic case, where we try and relax this to a matrix problem and see what bound that gives us. So the first thing I want to do is, just like in the quadratic case, I want to try and represent my polynomial as the quadratic form of some matrix. Can't quite do that, but what I can do is I can say that I can define a matrix M subscript f such that f of x is equal to by the way, I'm assuming D is even, this is 4, so this is just 2, right? Okay, so I can always define a matrix that satisfies this property. So if I plug in a tensor vector on the left and on the right, this quadratic form is equal to this polynomial. I call such a matrix representation of this polynomial. And there are definitely multiple representations. So like in the quadratic case, this matrix just needs to satisfy, aij plus aji must be equal to the coefficient of xi, xj in Q. But similarly in this case, we just want summation over ijkl. Summation over permutations of ijkl to be equal to the coefficient of xi, xj, xk, xl in F. Okay, so we have a lot of freedom on this matrix. And yeah, it turns out the higher degree the polynomial, the more freedom you have. Okay. All right, so this is a matrix. This kind of prompts the following definition. So last time, remember, we noted that spectral norm of this matrix A, corresponding to this quadratic polynomial Q, is actually just equal to the optimum of Q over the hypersphere. But here, notice that, since x is a unit vector, right, you're trying to optimize over the hypersphere. Since x is a unit vector, you have that the true norm of F is at most the spectral norm of MF. Since x is a unit vector, x tensor twice is also a unit vector. So that has to be true. Okay, so now this prompts the following definition, right? Where you define, let's call this the spectral norm of a polynomial f. It's the minimum over all representations of their spectral norm. Okay. And it turns out, I'm not going to go into the details of this, it turns out that the spectral norm of a polynomial is computable in polynomial time. And it turns out this is what the SOS hierarchy does on this hypersphere problem.
Do you require the matrices to be symmetric? Or is the best matrix always symmetric, or not necessarily?
I mean, you can show that for any good matrix, a symmetric good matrix also works.
Great.
Is that notation x to the circle x 2?
Yeah.
Is that defined here?
Yeah. Yeah, exactly. So that's the Kronecker product. Basically, it's so x tensor 2 is, x tensor x, yeah, which belongs to this. So it's a vector with tuples indexing its entries. Yeah.
So
it's just a list of the xi xj's.
Yes, exactly.
Of degree 2 monomials on X.
Yeah.
So in this polynomial, the exponent depends on the 4, does it?
Yeah, exactly. Yeah. So specifically for a general degree D polynomial, you'll write x tensor d over 2, mf x tensor d over 2. Of course, there's a transpose here. All right. Okay. So let's start with the warm-up. Let's see what we can do in polynomial time. So we know this is computable in polynomial time. So let's just use this. So we have f. It's a degree 4 polynomial. Its coefficients are non-negative. And let's show that you get an n approximation in polynomial time. Specifically, I'm going to show Alright, specifically I'm going to show this. And the proof is fairly straightforward. So take any matrix representing F. Alright? And let's bound its spectral norm. So it turns out that the spectral norm of this is at most, and this is a famous well-known fact, is at most the maximum row sum. So F has non-negative coefficients, so notice that you can create an MF with non-negative entries. So I lied when I said take any representation, I meant take any representation with non-negative entries. The spectral norm of this is at most the maximum row sum of this matrix. Alright? Okay. So this gives us an upper bound on FSP. Now we just need to borrow an F2 norm from below. So consider the following vector. X is equal to, so let the optimum row be I star j star, the row that realizes the maximum row sum. So I'm going to let X equal E I star plus E j star divided by 2, or let's say like 5 plus the all ones vector divided by square root n. Okay. So then let's just plug this in and see what happens. We know f of x is just x tensor to transpose mf x tensor to, which, because the non-negativity of both the vector x and m's entries is at least, up to constant factors. I'm going to neglect all constant factors in this talk. And in fact, throughout this talk, 2 to the d, 2 to the q type stuff is dust. Right. Do you care about q to the q? So yeah. Right. So generally, I'm going whenever I start defining vectors, I'll be very loose with them having constant length. I'm not going to make them unit vectors. I'll make them have constant length.
What actually is the interesting range of q for you? Where you're also most, I don't know, interesting, important or something?
So I mean, in particular, I guess it implies that after n to the n time, you have a constant factor approximation. Mm-hmm. And I think this cost is inherent. You have to pay this for being so general and for giving a result about all polynomials. Because this encodes some very hard problems, in particular sort of planted clique, which we believe you need at least exponential time to solve.
So q is like a power event, basically. Is the way you're thinking it.
Yes. So you can still do f, whatever you call it, in polytime, right? With q growing with n.
So it's in time n to the q.
Oh.
Yeah, right. So the spectral norm is defined with respect to the degree of f. So yeah. All right. So because of non-negativity, we have that this is at least E I star tensor E j star transpose mf times the all ones vector over root n tensor all ones vector over root n. Okay. So each of the 4 x's are entry-wise greater than these 4 vectors I replaced it with. And this is at least max row sum, because this vector is the same as E I star comma J star. This is the elementary vector in n squared with 1 in the I star J star position. So this just pulls out the maximum row sum divided by n. Because 1 tensor 1 is just the all ones in n squared. This gets replaced by that. And then you have a factor under. So we have this, and then we have this. So that gives you your factor and approximation.
Is it also obvious that when you're looking at the overall representation, you can pick one that has all positive entries?
Oh no, it's not obvious.
Oh, okay.
It's not obvious that the best one has all non-negative entries.
So,
Yeah.
but that still doesn't apply.
Yeah. So to give an upper bound, I just need to exhibit one good representation.
Yeah.
And that's what I did. Yeah. In fact, throughout this talk, actually, I'll be explicitly exhibiting the representations. So it turns out you might not need SOS to solve. But it turns out for the stronger results, you might the stronger version of the result, the square root of n over q, you need it. Yeah. Okay. Right. So now let's see what we can do in n to the q time. And we start with the following simple observation. That to show an n over q approximation to f in n to the q time, it suffices to show, well, force, spectral norm, the most.
Is 4 referring to the degree? Like if this was the higher degree polynomial with the 4 beta?
Yeah,
Okay.
exactly. Yeah, so we do this so that f has degree exactly q. Okay. So what's the proof of this? It's pretty straightforward, right? You just have f spectral divided by f2 norm. Sorry. Note that the following quantity is an upper bound on the true norm of f. This quantity is an upper bound on the true norm of f. So this thing gives us a polynomial time computable approximation. And then when you plug in this bound and take a forward cube power, you get exactly n over q. Okay. So we'll actually establish a claim much more general than this. We say that for any g that's homogeneous and of degree q, we'll establish that spectral norm of g divided by the true norm of g is at most n over q to the q over 4. This will imply our desired result. Okay. And of course, I mean that g has non-negative coefficients because powers of f have non-negative coefficients. Okay. Yeah. This is a more general claim. Now let's start with some warm up. Let's try and establish this claim when g is multilinear. Go on.
What do you mean by x to the q over 4? Is that like a polynomial?
Yeah.
Oh, so you take each thing to the q over 4?
Just power the polynomial.
Oh, you power the polynomial. Oh, you're assuming q over 4 is you're assuming q is multiple 4.
Yeah. Oh yeah, sorry. Q is divisible by 4 Yeah, in general, assume everything is divisible by everything in this talk when it doesn't make sense.
Yeah, in your last statement though, like 4 is like a magic number, right? It doesn't have to do with the degree of any polynomial.
Here?
G has nothing to do with the number 4, right?
Yeah.
Okay.
Yeah, that's correct. Yeah. All right. So let's try and establish the following warm-up result. G is multilinear, and it has degree Q. And I want to show that this quantity is at most Q to the Q over 4. Okay. And the proof is somewhat similar to the degree 4 case. Let Mg be its symmetric matrix representation. So you want to ensure that like in all the equivalent positions, it has the same value. So like in the quadratic case, we took Aij to be the coefficient of xij in Q divided by 2. So here it would be the coefficient of that tuple divided by Q factorial. Okay. So let Mg be, we'll call this SOS symmetric.
That's if like all the indices are different, like if some of them are the same.
G is multilinear.
Oh yeah, that's right.
Yeah. Good point though. That was a great point to bring up. Since G is multilinear, all the coefficients allow Q factorial equal. All the non-zero monomials allow Q factorial equivalent positions in this matrix. Okay, so Mg, let it be we'll call this SOS symmetric, specifically where Mg of I comma j is always equal to Mg of phi of I comma j, where I and j belong to n to the q over 2. Okay. So I'll call this SOS symmetric. Okay. So so take this SOS symmetric matrix representation. Now again we have that the spectral norm of G is at most the spectral norm of this SOS symmetric representation, which is at most the maximum row sum, which is just Perron-Frobenius or Gershkovin circle theorem. Okay. Now let's try and lower bound the true norm of G, and we're going to take the following vector. Let I1 star IQ over 2 star. This is the tuple indexing the best row of this matrix. Note that this matrix, again, just to remind you, it belongs to R n to the q over 2 cross n to the q over 2. Right, so I'm going to take the tuple corresponding to the best row, and I'm going to define my vector as follows. Star j 2. So note because of multilinearity, all these like I star j's are different. So this vector has length square root q, so I need to divide by that. Right? So this is a unit vector, this is a unit vector, so x has constant length. Okay. And I'm not going to like completely derive this. I'll just show you a picture, and hopefully that implies what you need. So we call it the final stops. So we have this matrix representation Mg. We know that spectral norm was at most sort of the maximum row sum of this matrix. Okay. now note that when we plug in x as this, by non-negativity again, we'll get x tensor q over 2 transpose mg x tensor q over 2 is at least the sum of the row sums over all equivalent rows. So what do I mean by equivalent rows? All permutations of this row. Okay. Note that these row sums are all the same. And why? Because I took mg to be isosymmetric. Alright. So when you plug this in, these elementary vectors are going to combine in all possible permutations. And I'm going to use this on the right. So I'm going to replace all the x's on the right with all 1s over root n. And I'm going to replace all the x's on the left with some permutation of I star. So I'm going to replace this with e pi of I star. All the stuff on the left. Okay. Note that we have this normalization to worry about. That's going to give you like square root q, roughly square root q to the q over 2. This is going to give you n to the q over 4. And so that's why this is greater than or equal to summation over q over 2 factorial rows, max row sum. Right, so like q over 2 factorial times the max row sum, whole divided by this stuff. So q to the q over 4, n to the q over 4. I apologize for the intersecting writing. Yeah. And this is exactly what you need. This is roughly up to 2 to the q type factors. This is roughly q to the q over 4 divided by n to the q over 4 times max row sum. And this gives you that approximation that you wanted. All right. So the multilinear case is pretty easy, right? So we get this in the multilinear case. But powering makes polynomials highly non-multilinear. So the question is, how do we fix this issue? Now, one standard technique, I guess, in the literature, so like one natural approach would be to do the following. You define this new polynomial. So again, let mg be the isosymmetric matrix representation of this polynomial. So you define this new polynomial as x1, where this is a vector by itself in Rn, tensor x2, so on till x tensor q over 2, sorry, xq over 2. So these are just indexing the vectors. Each one is a vector in Rn. Sorry. Yeah. So you define this new polynomial, where each one of these is vectors, and I'm going to try and maximize this polynomial over all xi being in the unit sphere. Okay, and it turns out that this quantity is within 2 to the q factors of the true norm of G. And moreover, this polynomial is actually multilinear. So this polynomial really is in n times q variables. It's multilinear. And it's within 2 to the q factors of this. And this is known as the polarization lemma. Yeah. So this would be a standard first thing to try. But this doesn't work, because you're going to try and use that result over there, where for multilinear polynomials you get this approximation. The problem is that you blow up the number of variables, specifically by a factor of q. So you get nq over q whole to the q over 4, which is n to the q over 4, and this exactly defeats what you were going for. Right. So we need to find another way of relating or reducing to multilinear problems. And we need to do this in a way that sort of doesn't blow up the number of variables. And that's essentially the main contribution in our work. Specifically, we we decompose a polynomial into a bunch of multilinear polynomials, and then we show that you can recurse on these multilinear polynomials, or like you can solve the problem separately on these multilinear polynomials.
Okay.
Yeah.
Is this the same as like dealing with the non-homogeneous case? Because if it's on the sphere, right, xi squared is 1, so you can get rid of it.
If it's on the
Maybe
hypercube,
it
then
doesn't make it not homogeneous anymore.
yeah, I think the difficulty is very similar to that. Yes.
I mean, I was thinking if you can deal with non-homogeneous, you can deal with non-multilinear, right?
Yeah.
Okay. And I guess probably converse it.
Non-multilinear.
Oh, maybe not. Maybe it's harder for the direction.
Yeah.
I thought maybe you could fix it up there.
Yeah, I'm not sure about the other direction.
Okay, yeah.
Okay. So let me state what we proved. This decomposition will seem a little weird, but hopefully in some time, if we have the time, it will become more clear. So you have a polynomial g of degree q. It's homogeneous and variate. Note that you can always decompose such a polynomial in the following way. Summation alpha. So I'm going to define what this is in a moment. These are multilinear polynomials. Okay, so in some sense, I'm just peeling off quadratic terms. Okay, so G2 alpha of x is defined to be summation so this is a degree q minus 2 alpha polynomial. I mean, q minus 2 times size of alpha polynomial. Okay? And it's going to be defined this way. X to the gamma times g to alpha plus gamma. Where, this is the corresponding coefficient of the original polynomial, little g. Yeah.
Is that homogeneous or?
Yes, it is homogeneous. Right. So I'm decomposing a homogeneous polynomial little g into a bunch of homogeneous multilinear polynomials. Note that the degree of alpha, or like the number of elements in the multiset, influences the degree of g to alpha and of this x to the 2 alpha. Okay. And the proof of this is pretty straightforward, right? I mean, if while you have a monomial with a quadratic term, just take it out common and keep doing this and group terms accordingly. So the proof of this is pretty simple. I'm not going to go into it. Yeah. So basically, we prove that this is the right decomposition. So what we prove, this is the main contribution of our paper, is the following. Basically, you can recurse on these multilinear polynomials. Okay. So why does this imply the result that we wanted? So recall that we wanted to prove that for any arbitrary homogeneous polynomial g, we get this. We only put this for the multilinear case. We wanted to prove this for the arbitrary case. So why does that thing imply this? Well, just decompose g like this, and then use that statement for multilinear polynomials there on each of these g2 alphas because they're multilinear polynomials. And then you just get maximum over this n over q to the t. This is maximized when t is q over 2. You'll get something. I'm making a mistake here. Yeah. Okay. I am making a mistake. Q minus 2t divided by 4. Right. Okay. And this is maximized when t is 0. You get n over q to the q over 4. Right. So note that t is 0 corresponds to, this like polynomial g of the 0 vector. Right? And this is literally all the multilinear terms in your polynomial. Right? So all the multilinear monomials in our polynomial fall inside this thing. So in some sense, it's saying that the multilinear part is the most troublesome part to approximate well. Okay. Yeah, so this implies a result. I'll try and briefly sketch why we take this decomposition and why it actually works.
How do you compute this decomposition? Is it really easy? Like, is it just like is it
Yeah.
like a pairing off?
Yeah. I mean, while there's a term with with the square term, you just take it out, and yeah, you can find out exactly what to group it into. Like you can look at each monomial and find out exactly what to group it with.
Okay.
Right. And yeah, that's it. So it just takes n to the q time. Okay. Right. So ideally, we'd like to approach this, in the following way. This, a two-part claim. Right. And for all alpha, you want to show. And by the way, I'm hiding 2 to the O of q factors everywhere, including here. Okay. Yeah, ideally we'd like to break it up into these 2 claims, but it turns out this is just not true. What does turn out to be true is that you can show this. So you can show a stronger claim on this side, where by this. So by this I mean the set of all tuples that have elements following this multi-index, right? And this is the size of that set. Okay, so this quantity is actually equal to and this quantity can actually be as large as q to the q, or like q to the theta q. So you need to be really careful here, like all the claims we're establishing, and and so we do that. And we're able to also establish this. Up to 2 to the q factors again. Okay. I don't think I'll have enough time to say too much about this, but on a high level, this claim, let's call this C1. On a high level, the idea for C1, and in fact, C1 is exactly what motivates our decomposition. It seems weird that we're peeling off quadratics or like square terms, but C1 is exactly what motivates this. And the motivation is this. Specifically, there exists a representation, mg of g, such that mg is the summation of block diagonal matrices. And few of them. Okay. So for a fixed T, this block diagonal matrix would actually contain the best representation, loosely speaking, of this polynomial. Okay. And so when you try and take the spectral norm of this, it's at most the maximum of the spectral norms of this for any given block diagonal matrix. And you took a sum over like few of them, so you lose the factor of few. Yeah. So this is what motivates this decomposition. I guess, I mean, let me try and give a simple example. Simplest example I can think of, let's do a degree 4 polynomial. Take the following degree 4 polynomial. Clearly, its maximum over the hypersphere is just exactly 1. Okay. Now, you can have multiple matrix representations of this thing. One matrix representation is to have you put a 1 in every position of the form I, j, j, and 0 everywhere else. This is one valid representation, just believe me on this. And here's another valid representation. Okay, I don't know why I drew the matrix. It's just the identity in, R n squared, n squared. So this representation has spectral norm 1, and it's faithful to our bar. And in some sense, it's a trivial example of this block diagonal claim I was telling you about. This representation actually has rank 1, and its maximum eigenvalue is actually n. And the reason for this is you can write it as the outer product of two vectors. So this matrix is equal to the outer product of two vectors, where this identity here is the n cross n identity matrix. Right. And you vectorize it, and yeah, so it turns out that this is exactly equal to this matrix. So yeah, I mean, in some sense, one can think of this block diagonal representation as following this kind of intuition. You want to kind of move all your mass to a diagonal. This polynomial is nice in the sense that it only has terms that appear with squares, but it turns out general polynomials you can do this approximately. You can pack it into blocks. Okay. Yeah. Right. We still have time to go over the proof of this. Roughly speaking. Okay, so how does the proof of C2 work? Well, we break it up into two parts. First, we'll establish G2 norm is at least up to 2 to the O of Q again. Okay. Second, we will pick y so that y to the 2 alpha is what we need. So, roughly stuff up to 2 to the over q. Okay. And so this claim is actually highly non-trivial in general, but it turns out in the non-negative case this simplifies a lot. And if y is non-negative, and we also know that G2 alpha has non-negative coefficients, so we know that its optimizer x bar of G2 alpha, let's call it x bar 2 alpha, the optimizer x bar 2 alpha of G2 alpha is also non-negative. Okay, this can be seen by a simple perturbation argument. Okay, so since this optimizer is also non-negative and y is non-negative, note that you can prove this claim pretty easily. Just take x as y plus x bar 2 alpha. Okay, this is a constant length vector. And literally just look at the expansion of G in this recomposition. I mean, it has the term x2 alpha, x to 2 alpha, G2 alpha of x. Right? So we plug in x in that term, and then we get that it's greater than or equal to y2 alpha, because this is entry y is greater than y. And this thing is entry y is greater than x bar 2 alpha. Right? And this is exactly equal to the 2 norm of G2 alpha. So we get that claim. Right? Now how do you pick a y so that y to the 2 alpha is this quantity? it turns out the following just works. Let's take y as square root alpha. That is, yi is square root of alpha I. Any questions regarding this? We heavily use non-negativity here. Like in all these steps, this inequality, that heavily uses non-negativity. The fact that x bar to alpha is non-negative also heavily uses non-negativity. So any questions?
What do you mean by y to the 2 alpha?
Literally this thing, right? I guess. I mean, in general for a vector, when I take vector to the multi-index beta, I mean product over I of y I to the beta I. Just like in the polynomial case.
This y is length 1 then?
Yes. Oh yeah. Sorry about that. It's a good point. So we proved that for all unit vectors y, you can show that the 2 norm of G is at least this thing, and then we just pick the appropriate y. All right, that's it. Yeah.
So then is the general proof structure also true when you don't have positive coefficients, or do you have to do like or do you have to do like an entirely different? It's just that the proofs are harder.
The structure is similar. So like even this structure is the same.
Okay.
But this claim becomes very non-trivial.
Okay.
The problem with the general case is like you have cancellations, right? So you can't use these like inequalities. And actually so this actually involves like some random roots of unity, Chebyshev polynomials, just to deal with cancellations.
But the overall proof strategy is the same.
The overall proof strategy is the same. Yeah, this claim right here is still used in the general case. Right. The only thing that changes in the arbitrary polynomial case is this claim here. You need to figure out what to do on multilinear polynomials, and once you get that, just plug it in there and you're done. Right.
So you lost like a square root of factor in this proof compared to your stated bound, right? Or like do you? What you have to? Is it easy to say like how you tighten it up to get that, or is it a lot?
Right. So okay, that's also one of the more technical parts, but. Loosely speaking, we didn't use the fact that quadratic polynomials are easy to optimize. Okay. If you so the bound I proved here for degree 4 polynomials, the n over q bound. If I generalize it to degree d, it corresponds to this n over q to the d over 2. Okay. And if you plug in 2, you'll notice that I get some polynomial approximation for quadratic polynomials, which is clearly crazy. So essentially we didn't use this fact that quadratic polynomials are easy. And so generally we proved this claim where if in some sense your polynomial encodes easy polynomials, you can exploit that. Okay, and get an approximation on the rest of it. So I'll be a little more formal. So we proved that if you can write a polynomial f in the following way, you can write it as summation x to the beta, f beta, where this is no longer a coefficient, this is actually a polynomial. Okay, and let's assume homogeneity. So, like all these betas are of a fixed size, d1, and this polynomial is of degree d2, and it's homogeneous. We proved that, so if f beta spectral divided by, f beta 2 norm is, is small for all beta, and not just this, for every, this should actually hold for every polynomial h in the span of the f betas. So if this holds, that for every polynomial in the span, you can approximate it easily, then sort of you get an n to the d1 over 2 approximation to this ratio on f. Okay, and that'll imply exactly the result we wanted. Now note that quadratic polynomials, like any combination of quadratic polynomials is still a quadratic polynomial, so it's still easy. Right. But yeah, this is more general. You know, it can work in general settings where like you just have stuff that's easy on a subspace of polynomials.
Just thank the speaker again.